So thank you, and it is great to see all of you, especially on such a sloppy evening out there. So I'm glad you managed to make it over here, and I'm delighted to have this panel as we wrap up our series, The Will to Meaning, Seeking the Why of Our Existence. We're going to be talking this evening about how we can look for a sense of meaning or purpose in our lives in light of what we've learned from the science of the cosmos, and I want to put this conversation in some context. Until about 500 years ago, pretty much everyone believed the Earth was the center of everything. And then came along Copernicus, a little bit later Galileo, who showed that the Earth was just one of many planets spinning around the sun. And our solar system was, in fact, just one of many star systems in our galaxy. And more recent discoveries reveal that there are at least 100 billion stars in the Milky Way galaxy, with billions more planets. And that's just our galaxy. And now there are some estimates that we just heard that there may be 2 trillion galaxies in the universe. And that's just our universe. Of course, there are theoretical physicists who believe there are actually a whole bunch of other universes out there, that we are in a multiverse, and there might be countless other universes. And human beings, well, we've been around for maybe 200,000 years, at least in some version of what we would recognize today. So to slightly misquote Humphrey Bogart, it doesn't take too much to see that the problems of a few people don't amount to a hill of beans in this crazy universe. We are just a cosmic speck, utterly insignificant in the grand scheme of things, or so it would seem. So how do you square the vastness of the universe with our own tiny place in it? I mean, does this bother you at all in some existential sense? And I have to say that I am looking for some solace tonight. I'm hoping that I will get something to hang on to from our distinguished panel. And we have a great panel who's going to help us out. So let me introduce our speakers. Paul Davies is a physicist, cosmologist, and astrobiologist at Arizona State University, where he runs the pioneering Beyond, the Center for Fundamental Concepts in Science. He also chairs the Search for Extraterrestrial Intelligence Post-Detection Task Group, so that if SETI does succeed in finding intelligent life, he's going to be there to tell us about it. He has devised and presented a series of BBC Radio 3 science documentaries and a 1-hour TV documentary about his work in astrobiology called The Cradle of Life, and he's the author of more than 20 books, including The Mind of God, How to Build a Time Machine, and The Fifth Miracle, The Search for the Origin and Meaning of Life. Ard Louis is a professor of theoretical physics at the University of Oxford, where he leads an interdisciplinary research group studying problems on the border between chemistry, physics, and biology. Previously, he was a Royal Society University Research Fellow at the University of Cambridge and the University of Oxford. He's also an associate of the Faraday Institute for Science and Religion. He's the author of more than 100 scientific research publications, and he made the 4-part documentary, Why Are We Here?, with filmmaker David Malone, in which scientists, philosophers, and writers discuss questions about meaning and the nature of the universe. And Lucianne Walkowicz is an astronomer at the Adler Planetarium in Chicago. She studies stellar magnetic activity and how stars influence a planet's suitability as a host for alien life. She was at UC Berkeley and Princeton before joining the astronomy department at the Adler Planetarium, and she is a 2013 TED Senior Fellow. She's now working on NASA's Kepler mission and is particularly interested in how the high-energy radiation from stars influences the habitability of planets around alien suns. And she's also a leader in the Large Synoptic Survey Telescope, a new project that will scan the sky every night for 10 years to create a huge cosmic movie of our universe. So great panel. Welcome, all of you. So Paul, I want to start with you.
Okay.
Does the vastness of the universe ever overwhelm you? I mean, do you find this exhilarating? Do you find it unnerving?
Well, it doesn't. Margaret Thatcher, the former British Prime Minister, if you remember her, was once asked, isn't it a bit daunting running a country with a budget of billions of dollars? She said, it's no different from running the household budget. The numbers are just bigger. And so basically, to anybody versed in mathematics, it's just numbers. And I'm not one of these
They're pretty big numbers, though.
They're pretty big numbers, but But we have big numbers and small numbers, and you manipulate them and you get results. For me, the significant thing is not the size of the universe. We're puny compared to that, though we're very large compared to atoms. We sit sort of in the middle. It's not so much that. I think what makes people stand out, and we'll get back to this, I'm sure, is our complexity. We're not proud of the fact that we're very large or very small. We're proud of the fact that we up here is the most complex system that we know. And to date, we're the only beings in the universe who can make sense of it all. And so that's really what gives human beings significance. And I'm sure we are going to come back to that.
Lucianne, let me ask that same question to you. Does the vastness of everything does it ever get to you?
I think for anybody who works on these topics, you're sort of faced with this balancing act, right? That if you really sit down and think about the enormity of the universe, sure, it can be very overwhelming. But the day-to-day of being a scientist, even if you grapple with something that is very big, you're very buried in your work, right? And so, looking at me from the outside as I do my work, I don't look like I'm contemplating the vast, cosmos. I look like I'm trying to get a computer program to work, which probably involves a lot of drinking coffee and possibly swearing and shaking my fist at the computer. So it's all very buried in the sort of gory human details, I would say. But every once in a while, I get a chance to sort of stop and appreciate the fact that we're talking about finding other worlds out there that orbit other stars, and that's very cool.
Because that's always a question I have about scientists is, are you so caught up in your work, your day-to-day projects that those big existential questions, you kind of just sort of shove them to the side? I don't know. Ard, do you think about these big existential questions?
I do a lot. I find them very interesting. I think it's what got me into science in the first place. I think the kind of drive to discover is linked to this drive of thinking about big questions. So I've always liked that. And to your early question about the kind of size of the universe, I remember, so I grew up in Gabon in Central Africa. When I was 7, I went back to Holland for a year. And we lived in flats, or apartments, you call them here. And I remember distinctly looking up at the apartments, and there's a whole bunch of them, and it suddenly occurred to me as a 7-year-old that behind every single one of those windows was another family, and my own life seemed very full and overwhelmingly full. And I suddenly realized that, and I could still feel the sense of, it was awe and wonder and fright all at the same time. When I realized that behind every single one of those windows was a whole other family with their whole existence, which was different from mine, but possibly equally rich, and it seemed just overwhelming. And that's just one apartment building. And then you start look around the city like this, and you see all this stuff happening. You look around this room, you see all these different people and their thoughts, and it's just an enormous amount of things happening. That it's not. Maybe it's strange that it took me till I was 7 to realize this, or said something about me. But it's struck me since then. So I think when it isn't just the size of the universe, the scale of it, that makes you feel small. It's the sense of other people and their lives and the complexity of it.
So,
cool.
So religion, historically, every religion that we know has its creation story, and science now has its own creation story, and roughly sort of the broad outlines are, it started with the Big Bang nearly 14 billion years ago, and then the Earth was formed maybe 4.5 billion years ago. Life came along maybe another billion years after that. Hominids, 3 million years or so, it started to appear. We sort of have the broad outlines, and I'm wondering how complete you think the story is, or are there still a whole bunch of gaps in the story? Paul?
Well, as you go back towards the Big Bang, it gets more and more difficult to be sure of things. So let me tell you, I'm so old that I was a student in the 1960s, and I can remember the professor who was helping me with my PhD giving a lecture about the Big Bang, which was well established, and about how the heat radiation left over from the Big Bang, if you sort of run the great cosmic movie backwards, you can go back to a time when the universe was very hot, and then you can think about nuclear processes in that intense heat, and that as a result of calculations, it would be possible to work out the ratio of hydrogen to helium based on processes that took place in the first 3 minutes of the Big Bang. And everybody in the room laughed, because it seems so audacious that you could talk about 3 minutes after the origin of the universe. You know, even the Bible just says the first day. So the first 3 minutes. But within 10 years, Steven Weinberg had written his famous book, The First 3 Minutes. And the point is that we can now, with the Large Hadron Collider at CERN, fleetingly reconstruct the physics, the events that took place in the Big Bang 1/trillionth of a second after the beginning. So after about a trillionth of a second, we're pretty sure we understand the physics.
But that first trillionth of a second, that's a mystery.
The further back you go, the more you need theorists like me as a guide, because we don't have the direct experimental access. And of course, everybody wants to know t equals 0. You know, what happened then, what made the Big Bang go bang, what happened before the Big Bang, was there a before, was it the origin of time, origin of space, is it just one bang among many in a multiverse? And we can talk about any of those things. We'd probably be here all night.
Aren't those questions pretty much all still up for grabs? Going back to the trillionth of a second and maybe before?
But many of my colleagues would say no, because they'd be very convinced that their version of events was the right one, but they don't all agree with each other. So I think it's an open question. What has clearly changed, the pendulum has swung in my career, is that the Big Bang was regarded when I was a student as the ultimate origin of all physical things, like Augustine, who said the world was made with time and not in time in the 5th century. Time itself came into existence with the Big Bang. Incidentally, so did the laws of physics. So did space. Everything all just sort of popped into being at that one instance. That was the party line up until about 20 years ago, when the fashion changed and people said, well, no, it's just because if the Big Bang is a natural event, if it can happen once, it can happen any number of times. So there must be many bangs scattered throughout space and time. So it's part of a multiverse. And so that's the fashionable view now. It's a more complicated one. I still, by temperament, prefer the single one with an ultimate origin. But the truth is we don't know. We may never know. It may be that this will be forever beyond our ability to come up with an answer.
So I'm interested in whether our two other panelists have any theory. Do you think we'll ever know sort of what happened at that original moment, or whether anything came before the Big Bang, whether that we popped out of another universe?
It's really hard, you know. One of the things, so I do a lot of public science communication because I'm in a planetarium, and one of the things that's complicated about discussing cosmology, these ideas about the origins and early development of the universe, is that it's where our language starts to break down. So a very common question is, what's outside the universe? And if you think about it, you know, the universe sort of by definition is everything that is. And therefore, if something was outside the universe and it was observable, then it would still be part of the universe. And you can kind of chase yourself around. And so, you know, you use that as a starting place and think about a universe as being a place with a certain set of physical constants or laws, in which case, you know, there's no reason that there can't be other universes that have different configurations from the one that we can observe. But it's really difficult to know. From an observational standpoint, the early universe is opaque, literally opaque to us, because of the physics at the time. And that means that, you know, it really keeps theoreticians in business. So,
So do you think, do scientists need a good creation story?
Well, so I don't actually think, it's a good question. So I don't know sure if the Big Bang is really a creation story, because the really creation story is where the laws of nature come from in the first place. And then, you know, it's perfectly possible laws of nature could have many Big Bangs, right? But that doesn't really explain the ultimate kind of ontological question, the philosophical question of where did the laws of nature come from in the first place. Maybe the laws of nature that made the Big Bang were preceded by a different set of laws of nature. Maybe they were caused by another set of laws of nature. And then you get into the kind of classic problem. So either there was an infinite regress of causes, which may be true, but would be different from anything that we have experience of. The possibility would be that, you know, these things popped into being out of nothing, but not kind of a vacuum, but true nothingness. So no laws of mathematics, nothing, right? Just suddenly these things popped into nothing. What's an extremely odd concept? Another idea would be that there exists some kind of necessary being. This would be the kind of classic idea of theism, so a being who cannot not exist, something outside of space and time that caused our space and time to exist. It's also an odd idea from a scientific point of view, but all three of them are odd, and you could probably think of other scenarios as well. And the interesting thing about this is that many are pushing on this question. It helps you see that there's always a step from science to some kind of metaphysics or some kind of theology. And so I think it's important for scientists when they start using the language of creation or creation stories that they don't mix these two things. Or when they do mix them, they don't mix them they don't wrap themselves in the mantle of science and make what are effectively metaphysical claims.
Do you think, and this is really directed to any of you,
Yeah.
do we in some, I don't know, psychological sense, some philosophical sense, need a creation story grounded in science? I mean, one that really holds up, that gives direction in our lives in some way.
But it doesn't have to be grounded in science. We just don't like loose ends. And so the idea that, well, we can explain the world in various ways, but how do you explain that? How do you explain that? And you push it back, push it back. I think Art is exactly right, that when it comes right down to the laws of nature or the laws of physics, as most of my colleagues like to think of it, almost all scientists simply, at that point, they stop talking.
Well, I mean,
they don't want to talk about
it
where the
seems
laws of physics come from.
inconceivable that we could ever know where the laws of nature come
Well,
from.
no, because there are more. We could bring the laws of nature within the scope of scientific inquiry if those laws are not fixed and absolute and don't have to be as they are. So one of the more interesting things, interests me anyway, is could the laws have been different? Could the universe have been otherwise? That's what Einstein said really interested him. Could the world be otherwise? And if it could be otherwise, we want to know, well, why is it as it is? Is that just an arbitrary thing, or is there a reason for why things are as they are? And then you get into the idea that there might be an infinite number of different sort of sets of laws and things, and perhaps only in a subset of those laws would there be any beings like ourselves able to emerge and discuss it. So that's one line of reasoning. But all of these things rest on something else. They're all like the Tower of Turtles. And if you imagine the Tower of Turtles, it'll be an infinite regress unless there's some sort of levitating super turtle that holds the whole lot up. And that could be, a necessary being, or it could be some sort of self-explanatory loop whereby the laws explain the universe, which explain the laws and observers in some sort of self-consistent arrangement. John Wheeler, the cosmologist and theoretical physicist, like that sort of idea. So there's a whole lot of things going, but I think we don't just stop and say, well, it all follows from the laws of physics, and it's not a scientific question to say where do the laws of physics come from. I'm perfectly, as Sean Carroll once wrote in rebuttal to me from expressing that point of view, very nicely, he said that we follow everything back to the laws of physics, and then it stops, and that's okay. I'm fine with that. I'm happy to accept the laws of physics just as they are and basically get on with the job, you see. So by temperament, I'm not happy to stop there.
Yeah, I think that's something that I would pick up out of your question, Steve, is that when we say we, like, who is we? If you look at any number of scientists, just as if you look at any number of human beings, we all have different desires out of what we want from the world. And similarly, I think some scientists are very happy to not dig into where the laws of physics come from, but rather to understand how things work. That's something that's always motivated me. It's why I work on things that are very practical, like stars and planets. I orbit a star, I live on a planet. It's very observable, right? And I think these other questions are interesting, but they're not, the subtopics that I pursue in my research don't directly grapple with them because it's not my primary motivator. And so, I think we have to be cautious anytime that we try to talk about groups of people who have very different personal histories and motivations as any group, whether it's scientists or not.
So there's a lot of talk these days, really over the last couple of decades, about the multiverse. And, it's certainly in vogue. All kinds of theoretical physicists think that there are all these other universes out there without a shred of empirical evidence, as far as I know. And I guess the question is that, it's sort of come to this through various elaborate mathematical determinations. I guess the question is the multiverse, is this really a finding or a conclusion of science, or does this approach an act of faith, do you think?
There are scientific models. You could have Andre Linde's eternal inflation, for example, is a natural mechanism for making universes. You can dream up universe-generating mechanisms. That in itself is not a problem. Then if you want to populate those universes with different laws, well, you can do that as well, because we know that the low-energy laws that we observe, the textbooks that we have contain the laws of physics. They're the ones we know and love, but they're not like the ultimate laws. They're the laws that we observe at the relatively low energies that we lead our lives. If you go into the heat of the Big Bang, they sort of meld together. So there will be some sort of super laws in this multiverse that would then nucleate bangs all over the place, and when these universes cool, they will cool with different sets of laws. You can do all that. You can write down the equations. You can sort of make that happen. But it's only pushing the problem up a level, because this superstructure, multiverse, or the thing that contains the multiverse, still has to have laws. Where did they come from? Did that have an origin, or was it just always there with the laws that just happen to exist forever? So you still get into the same problems. It doesn't really help you. There may be a multiverse. It solves some problems. I usually say 2 cheers for the multiverse, because I think invoking it, we've just explained everything as a multiverse, is really very silly. But it does explain some things quite nicely, but no evidence, no.
So Ard, do you want to weigh in on the multiverse?
No, so I think it's an interesting question. Actually, in Oxford, we've run a program called Philosophy of Cosmology, partially because colleagues were noticing that other colleagues were making pronouncements about things that had never been empirically verified, and there's a strong tradition in physics that, in the end of the day, there's many beautiful theories that have been killed by an ugly experiment. And so, and what was interesting is, so there is a step of faith in this, which is not an unreasonable one, which is that physicists believe in what we call the unreasonable effectiveness of mathematics. It's the idea that mathematics tells us something about the universe, allows us to peer much more deeply into the structure of the universe than we actually feel we ought to deserve. We deserve. And that has been very successful for us. That's what helped us predict. The positron was predicted by Dirac by taking quantum mechanics theory of very small things, relativity theory of very fast things, putting together, and out pops this thing called antimatter, which is discovered. So we have this history of discovering really fantastical things by thinking about them mathematically. And so then the idea would be, could you extend that to other universes? And so that's the kind of, it's a step of faith, but it's not entirely an unreasonable one. But the worry that colleagues have had is if you keep pushing that along, you keep pushing it further and further away, you get further and further away from experiments, you might be completely, utterly wrong. We've had lots of examples of where we thought we were right and it turned out to be just completely wrong once the experiments came. And so then it turns out that what you're doing is something new. It's more like philosophy in the sense that it's hard to empirically verify. That doesn't mean, philosophy isn't just thinking whatever you like to. It's got its own logic, its own rigor to it. And so it is a new kind of thing. And is it science or is it philosophy? I think we don't really know what it is.
Does that matter? I mean, do we need to draw lines between what is science and what is philosophy?
No, we don't, but we need to be careful not to pretend we're doing one thing when we're doing the other.
Steve, it's probably worth, for the audience here, just spending a moment to define the word universe, because we're sort of bandying it around. And it's really important it's used in many different contexts. So when in the opening remarks we were talking about the universe with so many galaxies and so on, what that means is that's the patch of space that we can see with our most powerful instruments, which happens to be very close to the volume of space which we could in principle see however much money we spend. And that's because there's a horizon beyond which we can't see because of the finite speed of light. So roughly speaking, in the 13.8 billion years since the Big Bang, light has traveled at most 13.8 billion light years. We can't see beyond that, but everybody assumes there is something beyond that, just like when you look out at the ocean and you see there's a horizon, you don't think, well, the world ends there.
So it might just go on forever.
Assume there's more of the same, it might go on forever. So one definition of the universe is just that little patch. The other definition is whatever's outside that patch going on forever. And then we're into this other one, which is the multiverse. That would be lots of, maybe each one going on forever, lots of going on forevers, but separate from each other. So So all these different definitions, you have to be careful which one we're talking about.
So we're talking about cosmic mysteries here. And another big cosmic mystery, might as well put on the table, is there life elsewhere on another planet? Will we ever know this? I mean, what's your best guess? I'd sort of be interested in sort of taking a little poll here.
Yes.
Yeah? We will know. We will find it or we will know?
What is the distinction between finding it and knowing? Yeah, so, this was once a question that was sort of just a musing of people. Is there life on other worlds? Are there other worlds out there? But we're really in a period now where just over the past several years, we've come to know that there are billions of planets in our galaxy alone, and that a lot of those must be small. That's what our data tells us, is that a lot of them are small in the sense of being something the size of Earth or Venus or Mars. And those are the kinds of places that we think we might be able to find life in the universe. Now, all of the sort of newest of the telescope projects that are coming online are all geared not only at finding more of those planets, but in looking for something that we call biosignatures, signs of life, usually in terms of looking at the chemical balance, the makeup of the atmospheres of these planets, that might tell us that life is influencing the composition of that atmosphere in the same way that, here on Earth, we have ourselves, we breathe in oxygen and out carbon dioxide, and plants do the reverse. Cows walk around farting methane out into the atmosphere. So we have an atmosphere that betrays the presence of life. So the question that I think is a little more unknown, because we know in principle anyway how to discover life, and so really it's just a question of where to look. But the other question that we have is complex life that is perhaps not just small microbial organisms, but life that does things like, have panels and build skyscrapers and contemplate its place in the universe and ask these kinds of questions. That's more difficult to know.
How would we know?
Exactly wrong.
How would we ever detect that other than, they come and visit us?
Maybe they have.
Can I first say, so Lucianne has articulated the party line, and I strongly disagree with it. When I was a student, that was the point of view I put. I think the big unknown is going from non-life to life. We have absolutely no idea how that happened. We don't know how to estimate the odds. You can't estimate the odds of an unknown process. It could be it's 1 in a trillion to 1 against per planet, in which case we're the only one in the universe. We have no idea what that number is. Now we can hope that it's 1 in 10 or something, but seeing as we don't know what the process was, it's very easy to imagine a sequence of events each of which individually is pretty rare, and there's 1,000 of them needed, and collectively they're so rare that this isn't going to happen more than once in the universe. When I was a student, that was the point of view. Francis Crick said, life seems almost a miracle, so many of the conditions for it to get going. And Jacques Monod said that, somewhat sexlessly, man at last knows that he is alone in the immensity of the universe out of which you emerge by chance. So the point of view then was chemical accident so bizarre, such a freak, that it will have happened only once. Then the pendulum swung, and now it's fashionable to suppose that the universe is teeming with life, but the science hasn't changed. We're just as ignorant now about going from non-life to life as we were. Now, you may...
That's very true,
yeah,
very true.
Right. So there's only one place where we can be certain we will find life beyond Earth, and that is Mars, and we know that because he's got there from here, not in our spacecraft, but just by impact ejector. So Mars will have been seeded with Earth life, and Earth will have been seeded with Mars life throughout its history. So that's one place where we can be absolutely certain we will discover eventually that there is or was life on Mars. That's not the interesting thing. We want to know, can life happen twice?
So I want to take a quick little poll here
so I've been
among the three of you. So your best, obviously this is pure speculation here, your best guess, is there life elsewhere, and if so, is there intelligent life? I'm just sort of interested in getting each of your takes on that. Lucianne, let me start with you.
if I can briefly respond
Sure.
And answer your question. So that is absolutely true, and this is
let me
but it is true though, and this is a question. What are the chances that there's life everywhere, and that I get asked a lot, and particularly, there's a little bit of like a nudge, nudge, wink, wink, like there's got to be life everywhere, right? Because there's all those planets. And it is absolutely true and an excellent point that we don't know. You can't do statistics with one example. And that's why astrobiology exists. So, it is true that we have a lot of places that we can look. And I think that if life is out there, that we will find it. And that was the thrust of my answer. What is my guess? Again, if guessing was good enough for me, I wouldn't be a scientist.
But you have hunches. I mean, every scientist has hunches.
I would say that I would like to answer the question that I am spending a lot of time on it. If there's nothing out there, I'm going to be sad. But, I also would fold into that that finding a past life or even extant microbial life on other planets within our solar system, which I do think we also have a great chance of doing. That I think is just as interesting to me as finding it in some ways even perhaps more interesting than finding it around other stars, although it's a close tie. So I would like to, is what I would say.
Okay. Yeah. Ard, what's your hunch?
So I don't have a very well-defined hunch yet. I think on the origin of life, so it's true that we have no idea how the origin of life happened, but the only one thing we do know is that it happened quite quickly on Earth. Not long after the late heavy bombardment happened, so that's just that it may be relatively easy to start, although as far as we know it only started once. There are all kinds of interesting things, like the genetic code is highly optimized, which suggests there was some kind of things happening before, that some kind of pre-Darwinian life. So there's all kinds of interesting hints going on. On the other hand, we also know that life is very fragile. It needs an awful lot of things to be right at the same time. So my kind of hunch, which is probably not worth taking a big punt on, is that I'd be surprised if there wasn't some kind of very simple proto-microbial life somewhere else. I'd be surprised if there was complex life, just because I would expect to have seen some signature of it in some way or the other. But
I think this rapid appearance is another fallacy, as Brandon Carter pointed out many years ago, because if life hadn't got started very quickly, we wouldn't be here discussing it before the habitability window of the Earth closed. So life, if you're going to have a planet with intelligent beings who discuss such things, it had better get going quickly. And you can put the numbers in, assuming that every step of the way is very, very rare. And the numbers are very consistent with what we know about the habitability window of the Earth. So rapid appearance of life is consistent with it being widespread. It's also consistent with it being very rare. Doesn't actually help us very much. I think we should look right here on planet Earth for another form of life. It's often called the shadow biosphere, because if life does pop up readily in Earth-like conditions, this is the most Earth-like planet we know. And
what are you saying? What does that mean, sort of a shadow version?
Well, it means that all life on Earth is not the same life. So all life on Earth so far studied is the same life, but how do we know we've studied it all? Most life on Earth is microbial, and you can't tell by looking at those little critters what makes them tick. You've got to delve into their biochemical innards. And mostly, 99.9% of microbes have not been characterized, let alone cultured or sequenced. We don't know what they are.
Wait, so I'm trying to figure out, are you suggesting there might be different origins of life here on Earth?
Yes, many, but you only need one other, separate origin of life, and they could be descendants of that, if you like, second Genesis event, still intermingled with the life we know and love today.
I think Paul's argument is basically saying if it's easy for life to start, then on Earth-like planets, it should have started many times, and you might see remnants of that, which I think is that's a very good argument. I mean, you should look for it.
Use molecular microbiologists are looking for life all over the place.
Well,
why don't they just look for this?
I grew up in New York, and I hear it's in the subways. So,
So just to sort of round out this discussion, so Paul, your hunch, will we?
Well, I've explained I will not answer that question because we don't know the process.
Okay.
So I can't. I can answer. I can make something up, but there's no informed guess. But what I do feel is that the next step, going from some sort of microbial life to intelligent life, well, we don't know how to work that out either. But at least we know the process that made it happen. It's called Darwinian evolution. So we understand that mechanism. one day we might actually be able to do the calculation and figure out how many billion years does it take. We can't do that at the moment, but we know what the mechanism is. We're going from non-life to life. We don't know what that mechanism is. So that's why I think the error bars are all in that step.
Now, one of the things that's kind of exciting right now is we seem to be at this moment where there is a new interest in going out into space. We just saw the remarkable SpaceX launch yesterday. Is that important? Do we need to send people out into space to explore at least our solar system, perhaps beyond? I mean, not just send robotic vessels out there, but actually to send people out there. Does that matter?
I think you gain certain things with each approach. First of all, I think the divide that people perceive between human exploration and robotic exploration is a false one. If you look at the history of, for example, reconnaissance of the deep ocean, for example, the exploration of Earth has always been characterized by humans working together with robotic probes. And so the thing that you might gain, for example, in sending people to space is you gain a little bit of real-time decision-making. You might gain some ability to do more complex tasks, not even if just for the fact that a human can do complex tasks, but that you can design something that might break and then could be fixed. Many times when we design things like Mars rovers, they behave in a very delicate manner, literally scratching the surface of the planet, or in these days doing some drilling, but they are designed in such a way to be a little careful of them because there's no repair crew, right? So you do gain certain things by sending human beings into space that you might not necessarily have. However, it is much, much more resource heavy to send people to space than it is to send something like a robot. You have to, for example, make sure the astronaut survives. And many of the places that we're thinking about going are very far away. And that's an experiment that we have very little way of testing for. The effects, for example, on the human body of traveling to Mars. We have data from the ISS, the International Space Station, but that even is not a perfect experiment for what happens when people live out beyond Earth. So, I think that there has to be strong motivation to have it be human.
Isn't this ultimately not a science question? I mean, we're not debating this question of, to send people out there because we want to see how far we can push the science. There's something deeply emotional, deeply attractive about the idea that humans could go out and visit another planet. I mean, it would be mind-boggling. Right?
I think that depends on who you talk to, though. I think I do a lot of conversations with kids and teens about envisioning themselves in space, and what you find is that the trope of every child wants to be an astronaut is actually not true. Go figure, kids are people. One of the great things is that I hear all kinds of opinions of, my favorite one was we should send Congress there, and if they can cooperate enough to come home, they can have their jobs back. So.
So does anyone want to make the case for the importance of human space travel?
Yeah, well, I think I've been an advocate of one-way missions to Mars for many years because I think that's the only way humans will ever go to Mars. The price tag is too great if you bring them back. This is not a suicide mission. This is setting up base camp for what will become a permanent human presence on the red planet. And over 1,000 years, I think we could build it up to be self-sustaining. Why would we want to do that? Well, one reason is as a sort of lifeboat. If something truly terrible happens here on Earth, at least humanity or our culture or something.
At least a few people get to survive there.
Right, but to be self-sustaining, you'd need a colony of many thousands anyway, maybe millions. You wouldn't do it for the science. I think it's pretty clear that that we could do a lot of the science, for example, on Mars robotically, but we would do it, as you said, for a human adventure.
I have a colleague who's a virus expert who basically says viruses are mutating all the time. At some point, one is going to mutate, it's going to kill us all. So he therefore advocates, some people living on the moon or on Mars to kind of separate us off, and it's when we all die.
But I think this lifeboat idea is very misleading in that it only works if you talk way, way, way into the future where a colony or any kind of established living space, an encampment on another world, is completely self-sustaining.
Right,
because the idea that people are going to go to Mars and then just be able to live there without resupply from the Earth, I think, is a false one for a very, very, very long time and possibly forever. So it's not the same thing as if you put people there, then you have a backup copy and then everything is magically fine. There's still billions of people living on Earth that then die. So cold comfort for them, I guess. But I think it's a very difficult problem to have a completely self-sustaining space. I would see it as being more possible on somewhere like Mars than somewhere like the Moon. But it's still very difficult. And a lot of the ideas that are out there are really just that. They're just ideas. Planets aren't empty pools, dry planets that you just refill with like a hose, and then it's exactly the same as it was before. Planets are very complex systems.
But so are humans. And I think one of the things that's often overlooked is that it's no good just sending astronauts and a few pigs and cabbages and things and let them get on with it. As I'm sure you know, there's more cells in your body that are not you, they're microbes and your own body. So you have to send all that microbiome, well, that goes with the astronauts, but then that's only part of the great web of life, of microbial life, which is incredibly complex, incredibly rich, and has all sorts of checks and balances. We don't know what is the minimal subset of terrestrial microbiology that could be self-sustaining on another planet.
We basically have to send our version of Noah's Ark there as well.
Right, but you have to have all those microbes as well, you see, and that whole microbial realm, as I said earlier, is not really understood. You don't know what is that minimal set. And so you might get there and, you've left one particular bacterium out, and then the whole system is unstable. We don't know what that is, and it's very, very hard to figure it out.
So I want to circle back to where we started, which was having to do with the vastness of the universe, however we want to define the universe, and this question of human significance. And there's a famous quote from Steven Weinberg who said, "The more the universe seems comprehensible, the more it also seems pointless." Would anyone want to agree with that? Is it pointless? I mean, it's kind of cool that we're here, but in the grand scheme of things, it's really pointless.
Yeah, I think you got it exactly wrong. I think the more it seems pointless, the more it would be incomprehensible. And the fact that it is comprehensible, to me, it suggests that there is something like a point. But
What's the point being that we can comprehend
there
it
is
in some
a
way?
comprehensible scheme of things, that nature isn't just arbitrary or absurd, that there is a classic example. I'm doing too much talking, you interrupt me.
Oh, I will if I want to.
The classic example is the Higgs boson. So the Large Hadron Collider, 8 billion euros, it wasn't built on a whim. It was built on a theoretical expectation, which from the 1960s, there was a rational scheme. It may not have been the right one, but nobody expected when you built the Large Hadron Collider you would find absurdity. You get to the next level down, you expect to find meaningful order. It may not have been the Higgs boson, may have been something else, but you wouldn't expect that everything's ordered and rational down and down and down, and suddenly it's all ridiculous. You couldn't be a scientist without, as an act of faith, believing that the universe is ordered in a rational and intelligible way all the way down. So that's an act of faith, just like people have an act of faith in a God or a necessary being or whatever it might be. You cannot do science unless you have a belief that the world makes sense and that human beings, at least in some limited way, can make sense of it.
So Ard, let me bring you into this. Is the ultimate point sort of discovering the underlying order of things?
I don't know if it's the ultimate point, but back to Weinberg's quote. So for a Christian like myself, it's kind of the other way around. So you think that the world is ordered and perhaps discoverable precisely because you think there's some creator behind it who made it in a certain way. And so therefore, the more you understand that, the more cool it is in many ways. And I think Paul's point is if you actually if it turned out that it was all chaotic, or you couldn't understand it and it was kind of fickle and strange, that would be surprising. If you started from the premise that there may be a God, it may not be surprising if you think there's no God, because then I think all bets are off. And so it's kind of the other way around. I don't actually think he actually believes that himself. I think that was just a rhetorical flourish. Of course, it's worked really well because you remembered it. I think that in fact, I'll take a step on, and a friend of mine who's a sociologist at Rice, Elaine Howard-Eklund's done probably the biggest studies of scientists, and she started out asking them about their religious beliefs, and turns out a lot of scientists have a lot of interesting religious beliefs, a lot more than people realize. But one of the things she told
Because, I mean, the assumption is often that with the subset of scientists are far less religious than the general population.
It's a complicated story. But I won't summarize her. But in fact, a lot of scientists are quite spiritually interested in things. There's a small fraction that are kind of rabid, hardcore atheists, and a large fraction have all kinds of other beliefs, often affected by their own upbringing. But one of the things she noticed in these discussions with scientists is that they all kept talking about the beauty of the work and the aesthetic, and so she's gone back and looked at this and redone a whole bunch of interviews across India, Italy, the US, and one other country, I forget which one it was. And you just find it almost universal. Scientists talk about the beauty and so the aesthetic draw is very strong, and actually it correlates positively with kind of how well established they are and how successful they are. The more that they're likely to use that beauty as something that draws them, something that motivates them.
The beauty meaning everything sort of fits together?
Yeah, so it can be, biologists tend to say it looks really pretty when looking at a microscope. Physicists tend to say there's something intrinsic about the way the math works together. It's very elegant. But the idea that understanding, so these are not things that they don't understand, these things they do understand, and the more they understand it, the more this draws them.
Which is interesting, because there is also that feeling that, will science explain away the mysteries, and will that take away from...
Unweave the rainbow. Yeah?
Exactly, yes.
Yeah.
But you're saying just the reverse.
I think it's reverse, and I think that is actually a pretty common view among scientists. So the kind of nihilistic thing you get from Weinberg, I don't believe that he thinks that.
Yeah, Lucianne, what about you?
Well, I think to me the feeling of being able that anything is comprehensible at all. The fact, that I often to point out to people is that it is a really amazing thing about astronomy that physics and chemistry work essentially the same. I mean, there's different domains here in labs that we can create versus what is out in space. But the fact that the basic physics and chemistry work the same in labs on Earth as in the deep cosmos is kind of what underpins a lot of our ability to learn things about the universe. And the ability to do that seems very profound to me. Now, there's a difference to me between saying that and saying that necessitates there being a point. I certainly feel like the orderedness, the ability to understand something about the way the universe works is very pleasant, but I don't know that it compels me to say that there's a point to the whole thing. It's a little like how my experience of imagine the most beautiful landscape you've ever seen, whatever it happens to be. As somebody who comes from a physics and astronomy background, I can look at that and see things working, and it's almost like having an augmented reality experience through my scientific practice. But would I say, well, what's the point of this landscape? Probably not, but I think that's something to do with my personality as opposed to it not being a good question.
So we're dealing with that very complicated word purpose here, and I think a lot of us would say that for us to go on living, I mean, if we really sort of have that existential bent, we need a sense of purpose. And sort of the question that we're asking here is, can science give us that purpose, or do you have to go outside of science to get that? And I don't know, does anyone want to make the case that actually science can help us come up with some sense of purpose?
Well, it certainly can if you use it by analogy or metaphor, in the same way that we are very comfortable in saying the universe is a machine. I mean, that's what Newton said, it's a machine, it's giant clockwork. Well, a machine is a human category, human invention. Aristotle thought the universe was a living system. today, a lot of people say, well, the universe is a gigantic computer. Nature is a computational process. All these are human inventions and human categories. The notion of purpose is a human thing as well. Humans have purposes, and animals have purposes. And so what I'd like to say is that the universe is not a machine, it's not a computer, it's not a living organism, but it contains some aspects of those things, so that these metaphors in a limited way do apply to what the universe is about. And purpose is not, an exact fit, but purpose-like or something, it seems to me, is just as valid as saying machine-like. It's just not as politically correct in this day and age to say the universe has a purpose. I prefer the word scheme, that there's a rational scheme of things that's intelligible. Whether that's a purpose, I don't know. Humans have purposes. We're part of the universe, so in some limited sense, the universe has got to have a purpose, if only from that. But I think the words, of course, mean different things to different people. And they're very
So Ard, you mentioned that you are a Christian,
Yeah.
and so I'm assuming that gives you a sense of purpose. But what about your science, your work as a scientist?
So I love science. I think science is the greatest thing that humans have ever accomplished. I think that in science, I'm really amazed that I get paid money to think about these things. It's people's tax money, so thank you very much to all of you. It's an amazing privilege. I love science, but I don't think and science gives me a purpose and something I enjoy doing, but it doesn't tell me a lot of really important things in life. Most important things are not solved by science. So why should I what is the value of a human being? Can I measure the value of a human being scientifically? Well, it's insane. You measure the value of the chemicals, like somebody with more gold fillings is worth more than something less. That's silly. Or you measure their brain power, or how the community values them, or how much economic output they produce. All of these are incredibly dangerous ways of measuring the value of people. I think human beings have intrinsic value that's independent of these kinds of measurable things. I personally think that comes because they are loved and created by God. I have many friends who don't believe in God, but nevertheless, we come to the same conclusion. I'm really happy about that. I worry sometimes about how they derive it. They probably worry about my faith in God. But I mean, that's an incredibly important thing about our life. And science doesn't tell me a thing about that, and it can't. Right? And so I think there's most important questions in life of that nature, the ones that you might put in the category of purpose, are not answered by science. That doesn't mean that science can't help us think about those questions by sharpening the questions and showing us what's a good way of thinking about them or not, but it doesn't give us the answers, and it never has, and it never will.
Lucianne, you sort of said that you get nervous if people talk about the cosmological evolution has a point to it. But do you grapple with these questions of sort of meaning or purpose, and in light of your work as a scientist? Is that relevant to you?
Oh, I don't get nervous if people grapple with whether something has a point. They're welcome to do so. It's just not something that is really at the forefront of my mind. I would say that I derive purpose not so much out of my work, so much as I would say that I derive a lot of joy out of my work, and I derive a lot of perspective out of my work, but I wouldn't say that my purpose comes necessarily from my work. I would say it stems more from interpersonal interactions with people and the things that I can do that impact people's lives in the world.
So I want to go to our audience in a little bit, but before I do that, I want to sort of dive a little bit deeper into kind of what motivates each of you as a scientist. What is the thing, if you could sort of generalize it, that especially drives you, that you're most passionate about in terms of your work as a scientist, that makes you glad or have joy in this profession? Paul?
Well, I was born a physicist, so it wasn't something I cultivated, so it's in my soul. I just think it's magical that you can write down equations and discover stuff that nobody knew before, and I just think it's fantastic. I wouldn't do anything else if I had life all over again. I often say to young people, because they never seem to know what to do, I say there's really only one decision you need to make in your life. Do you do physics or something else? And if it's something else, it really doesn't much matter.
So you knew from when you were a kid that you were going to be a scientist?
Absolutely, yeah. Yeah, the story I like to tell, seeing that I alluded to Margaret Thatcher, is that she gave me a star atlas when I was 16, and it's true. I have that atlas with her signature in it. And that's because she was the Member of Parliament of the school I went to, the high school in Finchley in London. And it was what's called speech day there, prize day, and I got this prize for doing well in my exams. And so I often say, well, that's when I knew that I wanted to be an astrophysicist or cosmologist or something. But it went back much earlier than that. As early as I can remember, I was just fascinated. I think what gets me, I mentioned about writing down equations and finding out things, hidden realities. So I was always fascinated by the idea that there's a lot of things going on that we don't see. I can remember as a very small child, reading about atoms, and so many of them, lined up, and they're too small to see. And I thought, well, how do scientists know about atoms if you can't get a hold of one? In those days, you really couldn't do that. Can now. But I was just fascinated that all these atoms sort of inside us, and we can't see them. And then invisible forces, electricity and magnetism. You can sort of feel them. You can't see them. What's happening here? And all that stuff, and neutrinos that go right through us, and and now we've got dark matter and dark energy. And I think it's just fantastic that there's all this sort of hidden stuff going on, but that we can make progress to unravel it, understand it, and discover about it. The most recent being the Higgs boson.
Ard, what about you? What's it, sort of, if you could look deep inside, what is it that motivates you as a scientist?
That's a good question. I just love science. So some of my friends and colleagues do science because they think it's going to improve human life, and so they might work on something where that's more direct. I do more abstract work, so I still think, indirectly, it might have a big impact. It might not. I may never know. I think I'm largely just motivated because I think it's really cool, and I can't believe that I'm so lucky that somebody would pay me money to think about this stuff, and so I pinch myself every day. I don't. It's not like I have to go in. Somebody has to say to me, "Oh, gotta go into work, gotta go do some research." It's like I'm thinking about it all the time.
But what is so cool about it?
Well, so this is an interesting thing. Almost every scientist you speak to, once they get into the little thing they do, it turns out to be really cool. It's like you look at something. So currently I'm working on, so I've moved from kind of quantum physics to thinking about life, and I'm trying to use ideas from physics to understand life. And life is just an unbelievably fascinating, complicated thing, and you don't understand it. And I have these. So currently I'm using ideas from computer science to think about evolution, and I just think it's really incredibly cool. It's like so beautiful. It's all interconnected. You discover these things. It's just a very fun thing to do. And I realized, being a physicist is always, great at cocktail parties. Probably not this cocktail party, but other ones, you stay here. What do you do? Your physicist kind of ends the conversation. So I used to say to people in that case, I worry about it, so you don't have to. But I just love it, and I think that kind of unique. Science is a competitive field because lots of people want to do it. It's also difficult sometimes. You have to work hard, long hours, and so you have to really love it, I think, if you want to go on. It's very fortunate. In my department, we have a bunch of retired fellows who are in their, so previous academics were in their 70s and 80s. They still come in all the time. They could go off and play golf or tend the gardens, and they do that as well. But they just love physics, and they love coming. They talk to me sometimes about what are you doing, and they get all excited about it. And I think when I'm 80 years old, I want to still be doing something like that I love. So, why do people love something? People love very different things. My father is a botanist, and he loves tropical trees, and he can talk to me for hours and hours and hours about plants, and it's something he just loves. And I'm very lucky, very fortunate that I live in a time when I can do this professionally. A few generations ago, I'd have to be independently wealthy to do this. So I'm very fortunate, live at a fortunate time.
Lucianne?
Topically, I think I'm very motivated by the search for life. I think it's one of the most profound questions, whether it's out there and whether we'll find it. As far as the day-to-day of being a scientist, I'm very motivated by the process of it. I like, as both of you touched on, the fact that any of it is comprehensible at all is really quite amazing. And I think part of the motivation for me as well is that I do, like I mentioned, a lot of public communication, and so I feel that the scientific background I have has really given me an enriched experience of my day-to-day and my appreciation of the world around me, or the cosmos around me even. And so I'm very motivated by an urge to share that with people and to bring them into part of that process. Not necessarily to turn everyone into a scientist, because I think that's a mistake. Not everybody wants to be a scientist. But this is a human undertaking that should be something that anyone can participate in if they want, or to appreciate its output in the same way that we appreciate things like literature and art in the world. And so, yeah, I'd say those are the big ones for me.
Okay, let us go to you. We have a couple of roving mics, so why don't you raise your hands if you have a question.
I know a bit about that because I just finished writing a chapter of my book about it. But also because I know the key players who've developed integrated information. Now, they don't claim that everything is conscious. You need a certain level, well, not only just a level of complexity, but a certain type of complexity. And integrated information is a way of putting a measure on that. And for example, you can have two circuits which are equally complex, just in terms of numbers of nodes and wires, and one could be conscious by their definition and the other not. So they have a way of quantifying the complexity, but it is the interconnectedness. And I struggled in writing this book to try to find a metaphor for it. And just very briefly, imagine a committee that is tasked with having to award a prize, say the Smith Science Prize. There are 20 members of the committee, and if each one just looks at the applications and votes, then it's not integrated. It's just a feed-forward system. But if there's some deliberation, some back and forth, people change their minds, some feedback going on, then it becomes more integrated. And if the entire committee arrives at a unanimous decision, that's like maximum integration. And so that's the essence of this, and it's a way of quantifying it. It's been criticized, but it's obviously a very good first step in trying to bring some sort of mathematical rigor to a subject that is otherwise really pretty flabby. And it's Giulio Tononi and Christoph Koch who are the key players, and they have some wonderful postdocs, some of whom have come and spent time at Arizona State University. I think it's terrific.
Mm-hmm. So I think Paul and I both reviewed some proposals on this topic, and so I think it's a really interesting idea because it's one of the first ones that tries to make something quantitative. Whether it's right or not is very unclear, but some people say it's one of the only games in town that's trying to make something quantitative. I think it's still very, very, very early days to see whether it means anything.
So, I mean, one of the questions that we really haven't talked about in the panel so far is where consciousness fits into this whole discussion. There is a strain of thought. I mean, going back to someone like the Jesuit priest and scientist Teilhard de Chardin, who would say that actually the point of all of this is that through these billions of years of cosmic evolution, we ended up with at least one species that has consciousness, and that's a pretty good reason for the whole story. I don't know. Does that have traction?
We don't know what it takes to make consciousness. So we assume that the swirling electrical activity up here generates consciousness, but the swirling electrical activity in the national grid doesn't, although we can't be completely sure of that. But what is it? Putting your finger on what makes it's not just complexity. It's clearly got something to do with the organization of that complexity, but we don't know what.
I can speak a little bit to that. So I'm spending a year at the Library of Congress. I'm the chair of astrobiology there, and I work actually on the ethics of Mars exploration. So I myself, obviously, am not a philosopher or an ethicist, but one of the things that I found really wonderful about being there is that my position is devoted to doing research at the intersection of astrobiology and its implications for society. And so it's afforded me the opportunity to read a lot of literature and to have conversations with people who are working in the realms of ethics, philosophy, law, anthropology, whatever you happen to name, whose work intersects with how humanity might live in space. That's not exactly the answer to your question, but I definitely do reference to the humanities and talk to my colleagues there as much as possible, because I find their questions and their viewpoints are different than mine, and it's very informative to do so.
Well,
Let me rephrase that question a little bit. Do scientists need humanists to do good science, to think well about science, to come up with good scientific problems?
This time tomorrow, I shall be having a discussion exactly like this at Arizona State University on the mystery of time with the philosopher Jimena Canales from University of Chicago. And
So
one scientist, one philosopher. So I do this.
I mean,
all the time.
make the case for why we need to bridge this gap between science and the humanities. Why do scientists need humanists?
Precisely because science is a human undertaking, and because there are what you might call non-necessary, like non-science implications for a lot of science research. One of the ways that this happens a lot in some of the fields that I work with is looking at data science and the uses of data. So in data science, anything that happens to either use your consumer data or more broadly can be used to analyze things like city data or population data, that has immediate applications to the way that people live in cities, and has applications to, for example, policies that might affect people's lives. So recently, there was a study that was done in Baltimore, which is where I'm living right now, that astrophysicist worked with the city to identify abandoned homes in the city. And Baltimore has a great deal of poverty. But there was no conversation between the scientific analysis that took place and any of, for example, the advocacy groups that worked in the city or in those neighborhoods. There was no community interaction whatsoever. And so the actual implications of what it means to provide the city with a list of abandoned homes, which often leads to things like gentrification that then push people out of their communities. The fact that there was no dialogue with people who were working within the sort of humanist side of what was happening in the city means that a scientific study took place in a vacuum, essentially, and did not, as the people who conducted the study, did not actually have the sort of benefit that they were thinking. And if they had spoken with people within the city to begin with, they might have designed it differently, and they might have seen the implications of what they were doing before it was done.
Well, it's true that the fine structure constant is 1 over 137.036 something or other, but I'm not sure that's very meaningful. I mean, there are a lot of facts that scientists uncover. Not everything that we find out about the world carries meaning. There's a lot of things that's just the way they are.
I mean, that's a fascinating idea to think that is science the vehicle to getting at truth? It would seem maybe one, but I don't know.
Most reliable path. Well, the truth, you have to be very careful. Don't spell it with a capital T.
Ard, do you want to take a shot at this?
Well, so I think people often ask this kind of question in these kinds of panels because, science is really amazing at getting certain types of reliable knowledge. So we've got pretty reliable knowledge about a whole set of scientific things that we've studied. And so it's tempting. It would be really great if we could use that same methodology to also adjudicate on all kinds of other questions, societal questions, questions about how we should live, what is the good life, what is not a good life, all those kinds of questions. And unfortunately, it can't. It doesn't mean it can't help us think about these things, but it doesn't tell us those kinds of questions. And so that's different from saying that therefore those questions don't have truth content to them. It's just the getting at the truth content is a lot more complicated, so we need to be a lot more careful about how we approach them and maybe hold things much more lightly. But I think most people actually believe that a lot of these things are true. So let's take, for example, your example of the study that was done in Baltimore and of empty houses. Well, there are all kinds of value judgments in saying, for example, it would be bad if these things got gentrified and people got pushed out. That the value judgment there is actually it's unfair to those people who are being pushed out. I happen to think that's a true value judgment, but somebody else may not think that, and then we should discuss this, right? Because there are people, apparently there are people in our society, sometimes more than we would like, that seem to think it's okay if we push these people on the side because, they didn't work hard or something's wrong with them. Which
Well, there are some well-known property developers.
Exactly. Well, I don't want to say anything about this country, but perhaps some locals. So, so those are value judgments we make that are hard, that we can't adjudicate that easily by science. But we have other values that ring in. I happen to believe that these things may be true, and I think Lucianne, you believe it's true by the way that you told your story, and so. And we have to be able to, but we have to be able to do more than just say, well, I happen to feel it that way. I have to give a good reason for why it's true. I have to give some, because as you see, there may be people like some well-known property developers from this town who may behave in different ways, and you can't just say to them, don't do that. You've got to give a reasoned and good argument why, and that is going to have to rely on knowledge we get from the humanities or from theology or from philosophy.
Generally, scientists are not good at confronting ethical issues, I think. And they often get carried away by their work, and they don't want any sort of constraints.
That's a fascinating statement to make, that scientists are not really very good at dealing with
I don't
ethics,
think
because so much of science leads directly to huge ethical questions.
And the one at the moment, well, two things at the moment everyone's talking about. One is unbridled AI. What should we put some checks and balances in? And the other is synthetic biology. It's fantastic. Some of my friends are making adapting existing living organisms in amazing ways, introducing additional nucleotides and amino acids and so on. I think it's all wonderful, and I hope they're allowed to carry on doing it. But who is to make the judgment about not only are these things risky, but are they simply wrong? Is it wrong for us to tinker in this way? I've got my opinions, but I don't think they're any better.
I mean, realistically, in either of those cases, do you think, because if you could do it, isn't there going to be this inexorable push to do it?
Somebody will do it, maybe in North Korea. And that's the problem. We might have wonderful regulations here, but we can't regulate for the whole world.
Now, there's things we can do. We can make bigger and bigger atomic bombs, bigger and bigger hydrogen bombs. We stop making bigger and bigger ones at some point. There may be other things that we might stop doing for some reason or the other.
There's a widespread misconception about quantum mechanics that, because quantum mechanics says that nature is uncertain, so that science is uncertain, and we simply can't say things. Quantum mechanics is very, very precise in what it says. It's just that it's the measurements that you make in quantum mechanics are statistically distributed and not deterministic, so you don't know in any given case. So quantum mechanics generally is not a recipe for saying science is unreliable. It's reliable in a very precisely defined mathematical, statistical sense. When you talk about the Planck limit, a lot of people are referring to Max Planck's pointing out that when you have quantum effects, you can combine the constants of nature, including his constant, Planck's constant, together in a way that gives a fundamental unit of length and time. And the length is 10 to the minus 33 centimeters, and time is 10 to the minus 43 seconds. And if earlier we were talking about the Big Bang, and you go back to the earlier and earlier stages, when you get to the Planck time and the Planck length, the whole universe is squashed into Planck length, then it's not that everything stops. We can't say anything meaningful. It's just that we have to then have a quantum theory of gravitation as well. And there are plenty of candidates for what such a thing might be like, but as yet not agreed. So there's string theory you've probably heard about, and then Jim Hartle and Stephen Hawking had some ideas in the 80s about that. So plenty of ideas out there, but nothing is yet agreed. So it's not a no-go zone. It's just that at the moment that really is the limit of what we can confidently extrapolate, even in our more speculative theories.
Maybe if I take your question a slightly different way, we should be to say, so we don't know what exactly quantum gravity is at the Planck scale, but does that matter for a lot of the science we do? Well, actually, for chemistry or for biology, it's largely irrelevant. So what you often think about in science is you have emergent levels that have their own kind of logic at each different level. And actually, the best way of thinking about them is at the level that you study them. And so even though you may not necessarily understand all the way down to the Planck level, it doesn't really matter because you have more or less what you need. And so for the kinds of questions that might have to do with the meaning of life or ethical questions, those would probably be, there's some kind of emergent questions that we're thinking about. And whether or not we do understand quantum gravity, I think will never have any impact on that directly. Indirectly, it might. Maybe quantum gravity might tell us something about the multiverse or not. Maybe tell us something about what the origin of time is. Those kinds of things. It'll get at those kind of big philosophical questions. But you don't need to know something all the way down in order to be able to figure out what it means at the level that you're interested in.
Sure, I can speak to that. So for anybody who's unfamiliar with Tabby's star or Boyajian star, this was a star that was observed by the Kepler mission, where what Kepler does is it looks for planets by measuring the brightness of stars very precisely and looks for little dips in the light of planets going in front of them. And Boyajian star was discovered to have a very unusual pattern of change in its brightness. That is now thought to be due to dust, but it caused this big stir in the literature because there was a dialogue about, could this be the sign of, large-scale alien engineering? And the source of this was that actually a group of non-scientists, through something called a citizen science project called Planet Hunters, was looking at these light curves, these measurements of the brightness of stars, and noticed this unusual piece of data, and had a whole conversation about it. And the published paper that originally came out didn't really have a good solution. And they had originally posited, well, maybe there's a giant cloud of comets around this star, and they're passing in front of the star and blocking it in unusual ways. And then another astronomer pointed out, well, you could also create this same signal by having some sort of large structure that obscured the star in some way. And so this became a big splash and a big topic of debate. As of right now, one of the things that scientific team did was they took follow-up observations. So the Kepler mission was no longer looking at that particular star because it's now in a different phase of its lifetime. And so they've taken follow-up observations, and they do believe that the variations are due to dust around the star, which is not tremendously uncommon, but it is the pattern of brightness that we see is just very unusual.
Could I ask you how recent that assessment is?
Like 3 weeks.
Because I thought this is wonderful, so I contacted Tabby and said, come and tell us about your star. And as of November, it still looked like there were some pretty odd things, including the fact that the star itself is dimming over the last 100 years. Oh
yeah, this is another really interesting thing about it. We tend to think of astronomy as being very modern, and in fact, the ability to have these big telescopes with digital cameras, which is what essentially we use for astronomy on them, is a modern invention. But there's also all this older data that can go back 100 years from photographic plates, and there's a big project at Harvard to digitize those. And so there is this long-scale dimming pattern, just a gradual fainting of the star over time, in addition to these sort of stochastic, chaotic dimming events. But just earlier in January, they came out with a paper that said it was probably dust. So.
I often say that there are three big origin mysteries: the origin of the universe, the origin of life, and the origin of consciousness. And the one we understand best is the origin of the universe, because actually it's very easy to imagine the universe did come out of nothing with space and time and everything else. That is not, for me, problematic. Origin of life, well, as we've said, it's all over the place, but at least we're hot on the trail. Origin of consciousness, I think, really haven't a clue.
Well, I haven't a clue. What a wonderful place to leave it. Thank you so much for coming. And thank you to our panelists. Thank you.